Hello, everybody. I guess we'll start, and if somebody comes, they'll be able to join later. I'm Renat Abdulin, and I'll try to share with you some of the cool and nice things that are happening in the .NET world with the relation to cloud computing and CQRS patterns that are emerging these days. And if there is a single thing that I want you to learn, or just to bring out of this conversation, is that there are lots of really interesting and innovative ideas to develop software. Some of them that may not be that commonly known. But these new patterns and new technologies that are emerging these days, like cloud computing showed up only recently, they enable small development teams or independent software vendors or self-employed software developers to build such astonishing solutions that are capable of delivering massive business value, helping people, improving economies, and the most fun part, competing with huge monopolies. And obviously, since that's the topic of my talk, some of these technologies belong to the field of cloud computing, which is in .NET world, Windows, Azure, and CQRS. OK, let's have the fun started. Boom, boom, boom. So the things that I will be talking about today are based on the practical experience that we had at Locat.com, which is a software as a service company, which is really small but tries to compete with huge competition. We're providing software as a service in the field of forecasting. So we're basically providing forecasts as a service. And in this field, we have to compete with huge established companies like SAP or Salesforce, which provide similar capabilities. And at the same time, I think we're doing pretty good. The company started a few years ago. For the CQRS integration projects, there are only 2 developers, but we're already delivering business value and moving forward. And partially this happens because to the flexible and powerful nature of .NET Microsoft platform and its cloud extension, which is called Windows Azure, and some of the technical patterns, designs, and ideas that are emerging these days from the field of CQRS. Having said this, I want to emphasize that this approach, it's not ideal. It's a simplified, practical approach to building solutions and systems on the .NET with the cloud, with Windows Azure. And since this is simplified and practical, it stems from our experience, which is, of course, limited. Since we're not a small company and we can't invest thousands and thousands of dollars into this research. What at most we can do is just investing a few hours of personal time to investigate, to write articles, which are then shared with the community. But as it turns out with .NET, again, with Windows Azure, this is more than enough to move forward. So basically, the first limitation of this approach, I know that's not a good thing, maybe to start the lecture or presentation saying that what we're talking about has a lot of limitations, but still. So this is practical approach from one small company that is still learning. We have only 3 cloud projects in production. These were delivered with extremely limited resources. They're working, and we're planning to keep on adding more. I will provide short coverage of them later. We don't have some of the things that I've been talking. They could be perceived as methodology, as mental model, as a way to look at the problems and challenges, maybe turn them into opportunities that prevent competition from blocking you from entering your field. But these things we don't have a lot of experience in teaching. Yes, we have this small distributed team of a few guys in Russia, a few guys in Europe, and they were able to comprehend and learn these things really fast without any previous background in messaging, in event sourcing, in domain-driven design. So at least this thing, although it might look as complicated, it's learnable, and you can start producing results really fast. Another limitation of this approach is that it requires startup survival mindset. So for most of the projects, and for the Locat CQRS projects that I've been mentioning, these are usually one-man-driven projects, and there are multiple projects driven by a single man. And in order to be able to work efficiently in this environment, not only you need to use methodologies like this one efficiently, you need also to have an efficient development environment, which includes such well-known practices as test-driven development, continuous integration, reducing low friction in all the fields of product lifecycle, starting from the actual development prototyping and up to the continuous delivery, all that kind of stuff. And obviously, every step on this road, every small part that contributes to the efficient development, it helps you to build solutions faster, more reliable, delivering more business value per person. And again, CQRS and cloud computing are one of these steps on this road. And the last thing that is really important with the CQRS and all the patterns that I will be talking about is that it requires a little bit of unlearning. So as a software developer with a few years of career, I started my journey in the world of .NET from the usual samples, like ASP.NET application that creates some sort of procedure and is basically a CRUD application, create, what was that? Create, remove, update, delete, something like this, that talks directly to the SQL database and maybe composes SQL query on the fly. This is actually the approach that I had to unlearn, because this is a real approach that works. It obviously works because there are lots of companies delivering business value. But in the cloud computing world, there are certain limitations and specifics that make this approach a bit obsolete. So this means that when you're entering the world of cloud computing, when you want to build amazing solutions with that platform, you need to be prepared to unlearn the things that you've considered to be true and established for long years. OK, so when we're talking about CQRS, Google usually says, have you meant cars? CQRS is a term which was coined by Greg Young. He will be presenting a bit later within this, what's the word, track. And it means command and query responsibility segregation. To the precise definition, it just means that in your system, which talks, for example, to the database, you're simply separating your read operations from write operations. And this means that by enforcing this separation, you're enforcing single responsibility principle, which latter allows you to optimize your read operations so that they will be extremely fast and work in the cloud, for example. And you're optimizing your write operations so that the data storage below the write side is really easy to work with, and you don't have a lot of problems, for example, while evolving this database. Or on a side reference. So basically, all the things that I will be talking about, there will be a lot of references. And at the end of this discussion, or on the links that I will provide, you'll find all the things. Again, if you're interested in this road, it will take you a bit of learning. So basically, what I've said about separation of reads from writes is just a basic design principle. However, if we look at the CQRS buzzword, which is obviously a buzz and hype these days, from an architectural perspective, it's a combination of a set of time-proven development practices that have been around for ages, for 10 years, for 20 years. For example, if you hear event sourcing, that has been around for a long time. And that's actually coupled with CQRS. That's how SQL databases, they implement replication, they ship transaction logs. So messaging, domain-driven design, and CQRS and event sourcing are patterns and elements which are well known and explained in the internet. You can Google them up, and they come together under the CQRS mental model to provide some simple understanding how to build systems, how to start building and delivering systems, maybe without being aware or worried about some technical implementations. So basically, it's just a simple way to look at building distributed systems that fit really well into the cloud. So just a quick overview of these terms to make sure that we're on the same page about the definitions. Messaging is really used in enterprise software, so-called enterprise software. Message is a data structure that has a name and has some parameters. It's sent from one server to another. The common implementation of messaging is web service call. No, web service call is not message. Basically, message is antipode of web service call or remote procedure call. In the remote procedure call, you send, for example, connecting to the server, you're saying, OK, I want to invoke this action. The name of this action is this, and I'm passing these parameters, and I'm expecting response immediately. Messaging takes a slightly different approach. Instead of saying, I'm invoking this method on remote server, and I want response back immediately, I'm saying, OK, I've prepared everything for you to invoke this method when you get time. And this everything is a message. Again, it's in the, for example, .NET world, it's a data contract that has certain fields. But unlike the usual messaging, we just send it up to the server, and it adds it to the queue. In the .NET world, the usual queue is MSMQ, which is used by all the popular .NET buses like NService Bus, Mass Transit, running queues. And then the server is able to process this incoming message when the time is due, when it's capable of doing that. This simple switch from direct method invocation to the messaging, it actually creates the foundation that enables you to build cloud solutions efficiently. Because in cloud, you have to build decoupled systems. You have to shift and distribute responsibility. Because cloud on its own, it's about resources which are provided to the customer. These resources could be processing power, storage, and bandwidth. And as you've probably seen from the news, the cloud is unreliable. A shortage on Amazon in one of the availability zones resulted that Heroku and lots of applications were down. Again, if you're developing for the cloud, you have to be aware of these problems. And messaging allows to decouple potentially failing systems in a temporal and geographical manner. Domain-driven design is extremely important as a development and design technique on its own. And it is, if you're diving deep into the CQRS, there are lots of terms that will not make sense until you're familiar with DDD. It essentially is a way of thinking and modeling your software in such a way that the resulting architecture will be actually matching to the real-world processes. If you have heard the terms of repository pattern, aggregate root, maybe value object, then these are terms coming from the domain-driven design. And if you heard, for example, the Magic Blue Book or the Blue Book of Tackling Complexity in Software, that's, again, the same book by Eric Evans, and it has essential and crucial influence for building cloud applications. Because it allows, first, to build and design systems in such a way that they reflect the real world, and that it's easier and logically simple and cost-effective to evolve the systems if you learn something new about this world. And second is that it allows to break down complex business domains into small pieces. They're called, for example, aggregate roots. So in a usual CRM system, for example, you can have a separate set of activities. You can have a separate set of customers, which are, for example, decoupled from users. And the importance this has for the cloud computing and building systems in there is that, again, cloud is about building distributed systems. And if your system is a big entangled system, then it will be rather expensive to scale it on the cloud efficiently or to distribute it. Domain-driven design allows to develop systems in such a way, to develop, design, and maintain afterwards. CQRS, it's the command and query responsibility segregation, and event sourcing is something that Greg Young will probably talk about later. It's not essential, but it has a lot of nice benefits. Okay, so from the architectural perspective, CQRS, we mentally or physically split our system. Doesn't work that well. Into 3 logical pieces: decide, act, report. This actually maps to the real-world business organizations, where, for example, you have manager that makes decisions based on the reports provided to him by his assistants. These decisions, he doesn't make them real by himself because obviously he doesn't have a lot of time. So he issues orders. These orders are acted upon by people in the field, and upon these decisions, reports are made. Again, these reports are then assembled by some more assistants and presented for the manager for further decisions. That's how large companies, they evolve and they move forward. Managers make decisions, some reporting department, some analytical department creates information for them in order to make thoughtful and sensible decisions, and there are always people, workforce, that implement these decisions. And CQRS is all about building systems this way as well. So if we map this logical structure to the CQRS and cloud computing world, is that the decide part is obviously the user. It's either the user on the web interface, it's either the user using Windows Forms application, WPF, Silverlight, or some cross-platform system connecting to the exposed API. They make decision using the information available to them, the views. And when they made the decision, it could be as simple as click rename button, or it could be as complex as a set of steps in a long wizard entry form. This decision is encompassed in a data structure message. However, in CQRS, we give different names, different meanings to the different types of messages. So in this situation, this message is called command. It says, for example, rename customer, or change customer address, or start analysis process. These commands are sent to the server. In Windows Azure environment, the sending process happens through Azure queues. Then the server side is a long-running process that continuously scans these queues to pick up new requests, instructions to do something. And when it discards this instruction, so it deserializes the message and invokes it against the specific handler. This handler actually does or attempts to do what the server has been told. So if we have a message named rename customer, so this message will contain all the information that is needed for the server to rename the customer. So it will have customer ID, old name maybe for validation, new name. And the server will be just loading the customer from the database, changing the name. That's it, as simple as that. And after changing the name, it will send another message to other systems, because the system is distributed and we're talking about messages and notifying other systems the usual pops up way. So it will send a message saying customer renamed. So this is what in the real world organization workforce does. So they accept a request to do something, they implement that, or if they can't implement that, they again fail, and they notify everybody else in the organization, all the interested parties, that something has happened. Then the reporting side is another long-running process. It could be hosted on the service bus, listens to these messages, and prepares reports. And these reports are completely detached from the from the act side. So it could be a list of failed messages. It could be a list of failed actions. It could be a list of customers that user attempted to rename within last 10 months or last 10 days and failed. It could be a list of users and customers in the admin dashboard. It doesn't matter. What matters is that these reports are easily consumable by the view side. And whenever user clicks on the next screen button or refresh button, he will have this latest data available to him. It might take a fraction of a millisecond. It might take a few seconds. And this seemingly long way of building something that could be implemented as simple SQL update statement is what actually makes efficient development over the cloud platform, over Windows Azure possible. Because it allows to scale and distribute applications and make them reliable and using efficiently all the cheap resources that the cloud computing provides. So while mapping this model directly to the simplest replication routes possible, so we can partition acting side, the server side, the workforce, by saying, okay, that all, for example, customers whose names, whose IDs, identifiers start from 1 to 2, they'll be hosted on this database server. All customers who have IDs 2, 3, and 4, they'll be hosted on this server. And then the message routing logic will know about that, and it will distribute the messages accordingly between these different servers. And what's more importantly, as our application grows and evolves, we'll be able to scale this system dynamically. So if we have, for example, huge popularity boost because we invented next Twitter, then we will be able just to say, okay, for all customers whose IDs start with 0, 1 will be hosted on that server. All customers whose ID has 0.2 on that server. And you can scale indefinitely. That's called partitioning in this case. Then events that are produced by the acting side, notifications, they are distributed between the nodes that are listening to that. So that's the reporting side. And we can scale it in a similar manner as well. First of all, we can replicate reports by just allocating multiple copies of the same report across the globe. It's really simple, and with Windows Azure, you actually have CDN delivery that uses, if I'm not mistaken, Akamai network. And what this means is that you can have, for example, the same report, which could be a list of current customers, a list of customers available to a certain manager. This data will be replicated around the globe. It could be sitting in a SQL database. It could be sitting in something as simple as a text file, or it can be sitting in a like protobuf serialized Redis key in Redis instance. It doesn't matter. We don't care about the technology. What matters is that this data is extremely easy to be consumed by the user application. It can be easily consumed by the web API. And we can replicate it as many times as we want because it's cheap. What it means is that, again, if we have influx of new visitors visiting our website, and as we know, 80% of the hits on the website is usually reads. So we'll have the data available for them for quick reads. If we discover that there are too much customers coming, these users and visitors coming, and we can't handle their load, so basically we can just scale out the information that is presented for the display, and we actually can also load balance for the user interface. And having said all that, the mere fact that you can scale the system massively, it doesn't really mean that you need to scale massively. It's just the side effect of the architecture, is just the side effect of decoupling. But if you happen to be next to Twitter or Google, then your homegrown system that runs initially on one single server, it can be scaled out. So what do we know about the capabilities that Windows Azure provides us for building such scalable applications? So Windows Azure is a platform as a service provider, which provides computing, network, and storage capacities on demand, which means that when you consume some resource, then you pay only for what you used. And the easiest example why it really makes sense, our company, Locad, will consume immense amount of CPU for forecasting. For example, at one moment of time, we can have just 10 virtual machines running unusual mode, processing the usual requests, and then the huge customer comes. And they have like 10 millions of products and the 5 years of sales history on that. So when such huge request comes, if we were using the same 10 servers, then we will not be able to produce report on that data within maybe a week. So what we do is just we ask Windows Azure automatically, could you please provide us 100,000 virtual machines? And we distributed the work between these machines. Half an hour later, the work is done. These machines are returned back. 10 years ago, this wasn't possible. If you are building a company, if you're, like, for example, young entrepreneur, young software developer that has an exciting idea and you want to change the world, but you discover that you need to invest in a data center or thousands of dollars into like some racks sitting on a backyard, it wouldn't be possible. You don't have that much money to invest upfront. With the cloud computing, you can. And the most exciting part, obviously, about Windows Azure is that it's native.NET, so it has wonderful integration capabilities with Visual Studio. You can build an application from the template, hit publish, and it will be deployed and running on Windows Azure. OK, so basically, Windows Azure provides a way to run processes. This process could be implemented as web applications. It could be as long-running service on the cloud, or it could be custom virtual machine. Technology doesn't matter here. The same is, and for the data storage, Windows Azure provides two basic types of storage, like SQL storage and NoSQL storage. That's about the implementation. And using all that, how we can distribute our decide act report model between the basic and the most simple form of CQRS application on Windows Azure. So for the client side, the side where we let the user decide to act upon the data, we can use web role, which is ASP.NET MVC2, MVC3, pure web forms application, it doesn't matter. Or we have been using WinForms applications, or you can use expose this data ability to act, to decide as an API. And the interesting part is that CQRS, since it explicitly delegates the deciding capability to a single point of logical point in the system, you can actually have multiple implementation of the deciding interface. Because when it goes out, it just sends a command. When it reads, it just reads the reports or views or materialized cache representations. And it means that for the same implementation, you can have the web UI that sends the commands and reads views. We can have Windows Forms application, which is desktop, but it accesses the same APIs and it sends the same commands and reads the same reports. And you have API that exposes all the complexity and business value of your system by accepting commands and allowing user to read reports. So this is just a side effect, but it allows you to achieve more with less. And actually, another side effect is that, for example, you can start building your own system, again, on your free time in the evenings, on the weekends, and don't care about having intricate web UI. As long as it works, it works. However, if that prototype proves to be successful in business, then you can just get the list of commands, get the list of reports, and ship them to the design agency, which are professional in creating really nice-looking UIs. And it will be already the specification for them to design something, to design UI. And at the same time, they will build a system that doesn't have complex business logic, and it doesn't have to be scaled, but it will be scalable because of the architecture. OK, time flies. So for the acting side, the service bus. In Windows Azure, we have basically currently the simple approach is hosting the bus on a worker role. Currently, you can use an service bus, which allows to work. And at Locat company, we're providing open source project called Locat CQRS, which has a simplified subset of the service bus functionality. Again, the technology, it doesn't matter because CQRS is technology agnostic. We don't care. So what happens here is that we have on the website, on the deciding side, some client that sends messages to the queues. The queues are in Windows Azure, Azure queues, obviously. And then we have worker process, worker role, that listens to these queues and acts upon them. Acting upon them requires having access to some data. And this data could be stored in a SQL Azure database, or it can be stored in NoSQL persistence that Azure provides. I'm tending to migrate my current projects from the SQL Azure database to NoSQL persistence because it's much easier to maintain and develop, especially when you're the only one that have time to work on this project. And when Greg Young will be talking, he'll be mentioning event sourcing. That's one of the techniques that allows to implement rich persistence schemas with really simple implementations. So when deciding side, again, long-running service process that acts upon incoming command messages, when we publish notification that something has been done, these notifications are, again, messages that go through the queues. And there is a same worker process that running, it could be running on the same machine. It could be running, again, on the same process. Or it could be running on multiple different machines. It doesn't matter, as long as we logically separate them in our system, and we can either keep them in one process or distribute between multiple machines. So this process receives incoming messages, and based on these messages, it updates views, which are used by the web UI for synchronous querying. And this triangle is essentially all the core stuff that is about building secure systems on Windows Azure. Oh, one side effect. Since CQRS as an architecture doesn't care about the technology, this system, if you build it, then it's potentially really easy to run the system on other clouds or on the local development machine. And that's actually what I have been doing with my projects. Windows Azure Development Fabric locally, although it's a marvelous thing, but it requires a bit of resources and it's slow. So for example, instead of running Azure application service in a Windows worker role, I just like it to run as a console application. The same one here. I like to run it as a console application, and actually these two are the same console applications. And for the website, what I'm doing, for the decide side, what I'm doing is I'm either using web UI, which is hosted in Cassini, like web dev server, or I'm using Windows Forms application. Again, such decoupling is just the tool, is a side effect that allows you to have more flexibilities in what you do and how you implement your solutions. And as a side effect, you might choose more efficient things. And another example, for example, we can have reporting side not run on the Windows or .NET framework. We can have it, I don't know, Ruby process, or the entire web UI. It can be implemented as a Ruby on Rails application. it doesn't matter because the only coupling points in the system are commands that go here, events that go here, and views that are being read by the client side. And as we all know, for example, protocol buffers, which is it is the fastest and most compact .NET serializer, or usual XML, as long as you have them defined, you can relatively easily, unless you do SOAP, interpolate between multiple platforms. A quick reference. So what the things that I've been telling about, these are based on the experience of building a framework to implement such solutions. It's Windows Azure. On Windows Azure, it's Locat CQRS. Obviously, it's one of different ways to implement that. And if you're interested in learning more, you can start using the framework, or you can use it as a reference when building your system, or use it as a set of ideas. So what we provide here is CodePlex and Google Code projects, which implement the actual CQRS engine, which means view handling, command processing, etc. We provide native work with Windows Azure Queues. We provide different kind of storage that are specifically designed for the building distributed applications in a concurrently safe manner. Provide additional testability. I'll have this information for the download. The actual, before I forget, so this is my website. And if you go to abdulin.com/publish/, then you'll be able to download this presentation. You can investigate it when there is more time, and we're running short. Okay, so just to provide you with a brief overview of what systems you can actually build with this approach, so how scalable it is development-wise, I'm just presenting three short case studies. This is the primary product of Locat. Its business value is irrelevant for us. What it matters is that it is a relatively complex application that has both Web UI and Windows Forms Management API. Windows Forms Management application. We didn't have any explicit API for that. It just happens that they share the same commands and they share the same views. This application is scalable and it is distributable. It can process, for example, 10 million, again, products with multiple years of sales history, and it will be processing them even when the data is retrieved from unreliable integration sources. What it does is essentially connects to a specific customer, discovers the database he uses, and based on that database, plugs the appropriate adapter, which knows how to pull the inventory data from this customer. Then this processes this data according to specific rules. Then this processed data is uploaded to the forecasting service. Then when this data is forecasted, we assemble it into a report and present to the customer. And all the sorts of blah, 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 and complexity that are specific to any complex domain. What matters here is that, first, we implemented this application using the CQRS and Windows Azure, and it allowed to deliver this project with a single person. And I think it took roughly half a year for me to do that. And the most time-consuming part was actually not building the project, but rather building the reusable service bus behind this project. So this project is multi-tenant. It can have really specific logic. It has full audit logs. It has full replication capabilities. And if we need it, we can easily expose third-party API to that. So this is the relatively complex application that has multiple interfaces. It was delivered relatively fast. It's reliable, and it survives in a world where, for example, customer's database could be a MySQL database, which is hosted on unreliable shared hosting with a few bare RAMs of memory. And such databases, they tend to time out from time to time, which happens almost every time. Another project. This project is similar to the previous one, but it deals with call center calculators. And what we learned with this project, it's possible to take a person who has not been working with the CQRS or Windows Azure before. We took a few guys from the UFA, which is in Russia. And .NET is not that popular there yet, so there aren't a lot of professionals. But these guys, they were able to build a cloud system in a few months. The cloud system was put into production, and customers actually use it, and we don't need to invest a lot of time to maintain it. It's actually running on autopilot. We don't have a lot of complexity when something needs to be changed or new business logic discovers. Again, because in CQRS model, you have explicit separation of logical pieces. And changing one logical piece doesn't necessarily require changing a lot of interlinked tables, for example, or changing the UI. Okay, and the third project. This is a currently going project, and it has its own specifics. It's a legacy system that has been designed using the really old technologies. So it's CRUD, it has a lot of logic in stored procedures, really complex SQL queries. I think the worst part was with 6 or 7 joins. And it's what you really called really brownfield project. And as we learned, it is possible to migrate such project to the cloud and to make it simple according to the CQRS, basically inherently adding scalability, ease of maintenance, full audit logs, ability to expose the functionality via API, etc., etc. And if you're interested, there's like the evolution approach in a few short terms. It was first we decoupled the system and the business side using domain-driven design. Then we're starting decoupling the web UI to use not the direct SQL database, but denormalized views to access information. And these denormalized views are created by the acting side, and the server side is itself being fragmented. Well, and obviously, the very first step was to introduce messaging and queuing. So what I've been trying to say here is that these are three slightly different projects. So one was a Flagman project with really complex. The second one was a relatively small project outsourced to a few developers that were not familiar with the concepts. And third one was core of a business that had a lot of business value. It had to be evolved step by step without taking it offline. It was all possible with this approach. And we have, as we speak, I think we have at least 3 more CQRS projects with Windows Azure, obviously, in plans, and they target slightly different scenarios. But so far, it seems to be working. And why this is important is that if developer has learned these principles, if you have learned these principles, it's possible to build a wide variety of systems that share the same features, which are scalability, ability to redistribute logic, ability to change business logic efficiently, ability to maintain it efficiently, ability to change technology without changing the entire project. And so you can switch developers, or you can switch between different tasks. And since we're talking about .NET, this means that you can develop business side domain logic using the same familiar development environment, which is wonderful Visual Studio. And you can have same teams sharing the same logic. So let's talk about a little bit about how CQRS scales. So obviously we have the performance scalability. We can distribute the load. We can, which is load balancing. We can replicate the read models. We can scale out the actual data side by partitioning. But in addition to that, we can also scale teams and complexity, which might be essential for small companies which are, or one-man companies, which want to deliver some project fast or outrun the competition. So from the team side perspective, this CQRS scalability means that you can distribute certain portion of the project to a different team. For example, you can have one person developing web UI and another person developing the server side. And they will only need to collaborate upon the message contracts that they will be sending and views that they will be presenting. And that's what actually we had done with the CallCalc project. So 2 guys, they were working remotely, not even meeting personally. And they were able to deliver the application using new technology within a few months. I think that was a nice success. And no matter what kind of team and approach you use, it's again the same set of mental patterns, the same set of technologies. And another important piece is ability to tackle complexities. As we all know, it's empirical evidence as the project complexity grows linearly, the cost or development friction of this project grows exponentially. And eventually, you might have experienced this already quite a few times. There is a certain point where complexity is so high that it's painful to change anything, because you never know what will break. Because you never know if you removed comment here, if the code will not compile. In C++, this actually was the case once. But because CQRS explicitly enforces separation of different logical concepts into different processes or just classes or namespaces or libraries, it reduces the overall system complexity. If you dive further into the CQRS, there'll be domain-driven design and different view models, different read models. They enforce simplicity as well. In the end, you end with code which is so simple that is almost boring. But more boring and simple code is, more easy and fast it is to write it, and less bugs there. OK, you could be able to download the presentation from abdulin.com/publish. So I'm not focusing on this one, and I have a little bit of time to show you in real life what the project might look like.
I have a question.
Yeah, sure.
Maybe it's not the right time. You said for the write operations, you wanted to use sharding, the example with some clients being in one database. So what if you have data that are shared between clients? We have kind of the concept of, we call them Uber clients. You mean clients that can control other clients' setup, and actually we can have multiple of those. So how would you have an idea how to solve that problem?
Well, basically, the modeling problem. So the problem here is to model the system, to design the system in such a way that it will be composed of partitionable pieces. And a book by Eric Evans, Domain-Driven Design, it's actually the thing that allows to build the system in such a way, to design and evolve them. Or maybe if you have like one complex business domain, which is interlocked, and you have Uber clients, you will be able to break it into smaller pieces. And when he was writing the book, he didn't care about the scalability. He didn't care about the cloud computing. He didn't care about the partitioning. He was just interested in making systems that are simple to write and maintain and easy to change. And so when if you have such a problem, then the first two steps is to make sure that people from the design team, from the architect team, they know about the domain-driven design, they have contacts with the domain experts, and they're able to gradually evolve your system towards the design where other Uber clients and usual clients, they can be sitting in one partition without big performance hit, or there is a way maybe to decouple that. For example, well, in ERP system, we have customers, we have invoices, we have orders. And naturally, coming from the SQL history, I would think that customer must have orders that he processed that are linked, because in the database, these are direct links. There are foreign keys and references. However, if we look at from a domain-driven design perspective, these items, they are not necessarily linked. So the same invoice, the same shipping order could be on the same server with the customer that they are linked to, but they don't necessarily need to have hard reference to that. So again, the question of how to design my system in such a way that the server side is partitionable, it's the question of designing it using the domain-driven design, which is the recommended and the simplest approach that I know. OK, now just to give you a quick visual representation. So this is Web UI, which is ASP.NET MVC using AutoFAC and Locat CQRS service bus for handling the messages. This is a simple listener that is connected to the service bus on the server, and that just listens, intercepts all the incoming messages. Oh, by the way, and actually, as Mark was saying before about the cross-cutting concerns. Nice thing about the message approach is that applying cross-cutting concerns is inherently more simple, because you already have the specific message class. So to each incoming message, you can apply security rule, which is based on a customer identity, or it can be based on the type of the message incoming. To each incoming message, you can apply auditing, you can apply logging, etc., etc. You can apply, for example, fail mode handling, which we actually use a lot. Fail mode handling, for example, means if we're connecting to the remote database, we want to retry the connection a couple of times, no matter at what stage does the synchronization fails. Since in our case, database synchronization is split into small pieces, and each piece is invoked by separate command. So when we start synchronization process, it's just a chain of messages being processed. And if one of the messages in this chain fails due to some problem, then we can, actually we don't do that. The system, it knows that it retries all the messages 4 times. So, and surprisingly enough, this handles of 90% of any connectivity or discovery issues that are bound to happen in such a volatile space as internet. Like services can die, DNS name can change, admins can change password, etc., etc. Okay, so just to have a quick view. So this is the web UI where a user is entrusted with the power to act, to do something. Well, let's do something, if you'll let me. Okay, let's start a long-running process called refresh solution. What this actually does, it sends a command to the server saying, do something. And it contains all the information to that. And as we see, this is the trace listener connected to the Azure queues. Server starts doing something. The green are commands. Blue ones are events. So basically, the green, each line is a message that has been sent. And it contains instruction to do something, and it contains additional information saying how to do that. And these are not the real actual commands, but these are textual representations, because it's easier this way. And when we have something happened, when we first request something, then there is information about something has happened. And what this actually means. This is the simple utility that I've built to simplify navigating the complex systems. It will be ported to open source within the Locket CQRS sometime soon. And this is, for example, is a single message, is a single command. Actually, it's just textual description of this command. So it can be represented as data contract, it can be represented as XML contract, it can be represented as protobuf contract. It doesn't matter. In this case, I just chose to display it as a protobuf description. And as we can see in the very top, there is a message called dataset part uploaded event, which has some domain knowledge, domain-specific meaning, and it is consumed by a few handlers. So again, we have a sort of cross-cutting concern here. So it is primarily consumed by the command handler, which is responsible for acting upon this command. And it is also consumed by 2 more generic handlers, one of which reports poisons. Basically, if it detects that a message has been retried too many times, then it's probably worthless to try it 10 more times. So it just drops it and reports directly to the support, which happens to be my mailbox. And the last is route messages. So if we want to have scalable system, and in this case, we do have simpler routing. So the message could be split between multiple processes, not split, but routed to one of multiple processes based on their availability. And so this is event. This is one of the commands. So when user side sends a command, when user sends command, server side acts upon this command, and the acting upon the command is actually where business logic resides, where it's the most interesting and exciting part for the developer to write. The rest is boring. And when we're acting upon the command, we're sending events. Event is, again, a message, and it is used by the server side to build reports. Reports are like this. In case of this system, I'm having a report as simple JSON files that are stored in Windows Azure blob storage. And these simple files look as boring as this. I could have used XML, but I found it more easy to read. So when I've been saying that CQRS processes the reports, processes the events, and builds and updates reports, which could be put to different servers or distributed between multiple geographical locations. Reports are just serialized representations of what we need to display on the screen. So that's actually the thing. So if I call, for example, a rename solution command, what it will do is basically send the message to the server. The server will access the direct database storage, change the name of the solution in that database storage, and then send the event saying that the solution has been renamed. Then on a separate process, or which could be like process thread within the same machine or a different server, we will receive this notification and update the reports. In this case, we have at least one report, which is a solution detail view, or we also have a list of solutions, come on, which has the same name. And we can also have a full list of solutions in the entire system. We can have also a full list of solutions that are currently running in synchronization. It doesn't matter. What matters is that we can keep on adding these new types of reports as the requirement arises. And for example, if I asked to build a report that displays all solutions that have first name starting with L and which are currently running and which belong to the user coming from Rwanda in Africa, it will be relatively easy to do that because all the information to build such a report is in events. I don't need to build complex link queries. I don't maybe even need to add indexes or, I don't know, do all the horrible things with a SQL database. I have events already that have been processed by the system. So I just take the full log of these events and build a report handler that denormalizes these events into a new type of report and add a UI which will be able to load this new JSON file and display that. Okay. So what else was the exciting part I can show? Well, that's, I guess, would be it, just barely scratching the surface. Oh, one more thing. Speaking of the audits. So you had the console listener representation, and this is the main log. It's just another way to represent the flow of events that have flown through the system as messages. It's continuously updated, and I can, based on this information, I can define custom reports on the user side, and I can build, for example, Excel reports for the admin that represent how many hours, for example, this customer cost us of user processing data, of CPU data. And so on the left side, this is list of messages. On the right side, this is what message is. It's a data contract that is identified by the name. It has certain fields in it. So if I was asked what is the most important component in the building secure systems and deploying them to the cloud, and building systems that can handle all the loads, scalability problems, and be developed with one single person. So the most important part is messaging, because it allows you to decouple systems in an efficient manner. Everything else is just tools and guides and patterns that allow to shape this decoupling to prevent it from turning into a mess of decoupled small instances. Questions?
How do you handle security between the components of the system?
Well, basically, it depends on what type of security you need to handle. So, for example, when a user when user is accessing the web UI, he is authenticated against the user store, and he has his own identity, which is trusted. So this identity is included into the message that goes to the server. And server knows that before performing certain sensitive operations in the command handler, it has to check if the user really belongs to that identity. And what more, we also include the information about the user into the event that has been published. So we can have full list of operations invoked by this user. Another side effect is that we can easily protect ourselves from hacker attacks. So, for example, if a malformed message is coming from the server, so with the wrong token or with the wrong identity, we don't do anything. We just simply drop it. So if you're a hacker that's trying to work around the system and hack it in some smart way by doing something that is not allowed in the usual UI, then you will have a really interesting situation, because if you do something wrong, you don't get any response. Nothing happens. And then there are also questions of securing channels between different systems, between, for example, right side and view side. And again, this is handled on a system by system basis. So if you're building a simple website that runs on your machine and you're a single developer, you can just secure it with one Windows Azure password. If you're distributing the system between multiple machines, you can make sure that a certain server can access only like the certain resources and have the routers route messages between these servers according to certain rules. And you can also have per-message decryption, asymmetric decryption of data, asymmetric encryption of data, of messages, etc., etc. You can add per-message rules, per-user rules. It all is doable because the system is already distributed, and you can play with the parts as you want. We have 4 minutes. OK, more questions? Yeah, sure. One problem with the session state is that it's a bit hard to scale, especially on Windows Azure, where when you want to have multiple web roles, you need either to have shared session state, which is impossible, or you need to use something like SQL persisted session state, or they're rolling out, what's the word? Session state based on Windows cache, I think. Yeah, Fabric cache. In this case, the advised approach is to use session as less as possible. And if multiple web roles need to access the same session state data, then you can persist it in something inherently scalable, like blob storage, trying to keep one single screen to one purpose, thus reducing the amount of round trips you need to perform certain action. And Windows Azure Fabric on its own will handle the scaling of the blob storage because it's scalable per container, I believe. OK. Anything else? OK, I hope I haven't bored you to death with this one. Well, thank you for listening. Thank you for coming here. Obviously, I've been just scratching the top part of that. But fortunately, there are lots of resources on the CQRS. There might be even a book by Greg Young coming out soon. And we're trying to share all the information that comes is open source projects with the articles. So if you're interested, just don't hesitate to come to forums, try the projects, provide feedback, and this will help us to make the world a little better. Thank you. And if you need, I can also, like business cards, just come and get one.